From the Library of Congress in Washington, D.C.
And I'm going to be the commentator for today, and I call this the nepotism section because we're going to hear from everybody who's ever held Nathaniel's job before him. You're in for a treat today. But seriously, we're going to hear from two wonderful astrobiologists, and the first is David Grinspoon, who is the senior scientist at the Planetary Science Institute and a tremendous writer. A lot of you would have been familiar with his book, Lonely Planets, The Natural Philosophy of Alien Life, which won the Penn Award for research nonfiction. And he has a new book coming out in December called Earth in Human Hands, and be sure you all buy that. Put that on your Amazon wish list. I'm really excited to hear David speak because I remember as a young boy reading Cosmos by Carl Sagan, the illustrated version. And the one thing that always stuck in my head were those pictures of different forms of life that could be found in the universe, and the hypothetical forms of life. So I think astrobiologists have always been confronted with that question, what is life, when they begin to think about what life could possibly be like outside of our own planet. And for most of us, I think we would answer that question by saying what the judge once famously said about pornography, that I don't know how to define it, but I know it when I see it. But I think an astrobiologist would say that we might actually not be able to use that definition. We might not know it when we see it. It could be so different that it makes the depictions of hypothetical life that Sagan once put forward look rather mundane and quite like our own. And I think David is going to talk about some scenarios in which life could exist in ways that, well, we might not have even defined it as life in ages past. So now I hand it over.
All right, thank you very much, Bill. And thank you all for making it back from lunch. I'll try to keep you awake while you digest. And I just want to start by saying it's a thrill to be back here at the Kluge Center. What a wonderful palace of scholarly wonder this is. And my experience here was great. I like to think that it's not just nepotism, but heritage that is responsible for the inclusion of the past chairs, and who knows, in 20 years it might be pretty crowded if there's a tradition here of inviting them all back. I'm here, I think, to represent the astro part of astrobiology. We've heard a lot of bio and a lot of chem, and I'm actually not someone that the traditional picture of an astronomer that goes to a lonely, cold mountaintop and looks through telescopes to try to figure what's happening on distant orbs. But what I do is I work with teams that build spacecraft and send them to other planets and try to figure out what the environments and the histories of those planets are, with a focus on the question of habitability. Where might there be good places for life elsewhere in the universe? Which begs a lot of questions, some of the questions we've been grappling with so far today, such as was mentioned in that wonderful introduction, what do we mean when we say life? Maybe we'll know it when we see it, but is that good enough? Now, as an astrobiologist, of course, what I really want is what Spock has here, a tricorder, so I could just point it at a planet or a potential life form and say, it's alive, Jim, or it's dead, Jim. I'm not getting life form readings. Is this thing working? But we don't have one of those yet. And it's hard to even imagine that we will have one of those someday, but maybe that's just because our science of astrobiology is in its infancy. We are in the pre-discovery, the pre-contact phase. Maybe we'll always be in that phase, but obviously if we're ever not, then our science will be very different, the way we approach questions like this. But as it is now, we have a real paradox with regard to this question. I'm not going to go into detail on what is life because I think actually Stephen Dick, who follows me, is going to talk about this a little bit more. But I do want to point out, because it's relevant to what I'm going to talk about for a few minutes now, which reminds me I need to start my little timer here because there isn't one otherwise. Excellent. I want to point out that the paradox at the heart of this question for scientists and scholars and just conscious beings in this pre-contact, pre-discovery phase, which is that we're searching for something that we can't really define. How do we define something when we only have one example of it? That's not really a very scientifically credible thing to do. If you're going to put something in a classification and say what its properties are, then hopefully you have multiple examples of it. Well, maybe we will someday. But as of now, we're searching for it. And when we find it, we'll be able to define it much better. But that's kind of weird, searching for something that you can't say what it is until you find it. So there is a little bit of a paradox here, and we grasp at things like we'll know it when we see it. But we're not completely stuck. There are useful things we can do. For example, we can talk about searching for habitable conditions elsewhere. We can't say exactly in an ironclad way, perhaps, exactly what life is, but we can give our sense of what it needs. It seems like needing an energy source is pretty safe. However you define life, it's going to have to eat or consume something, because if it's not doing that, if it's not using energy and metabolizing, then, you know, what good is it as a life form? I don't know. I think that's pretty safe, that it needs energy. And then you get more towards life as we know it. It probably needs some liquid medium. Maybe it needs water. Okay, we're narrowing our range of assumptions, but it still gives us something concrete and reasonable to search for. So the conditions of life is something we can try to define and search for, even if we don't quite know what it is. We can also look for what Spock would call life signs, but that is life, again, whatever it is, must be something that somehow perturbs its environment. And there are more specific ideas about this, not to get way into it, but the idea of chemical disequilibrium, that life is something that messes with the chemical balance of its home planet. Certainly Earth, the one planet we know of with life, is flagrantly disturbed by the presence of life, so that the atmosphere has a composition that you, as far as we could tell, I mean, I'd put money on this, even while admittedly we're in the pre-contact phase, we don't know anything. I'd put money on that we will never find a planet with an atmosphere as weird as Earth's that doesn't have life. That's a life sign, an atmosphere with mixes of chemicals that should not be there due to any other reasonable process. So we can talk about life signs. And then, and this is something I'm barely going to skirt on in this talk, but certainly if there was an alien species looking at our planet, they would notice also something else is happening to our planet. We can search for signs of intelligent life, and that's another thing I put in quotes, because do we really know what we're talking about when we use those words? It's an interesting question. But that's certainly something I think in this whole spectrum of things that we might find elsewhere that betray the presence of organisms, we shouldn't completely ignore. So there's another paradox, couple of paradoxes we encounter with this question, and that is when we go towards scales that are very small or very large. We can come up with reasonable definitions of life, but there's a strange thing about life when you go to different scales. For instance, in this graphic I've shown here, this human being, I think we would all agree, is alive. it's composed of cells that I think we would all agree are alive. They're very similar to living organisms that aren't part of larger organisms. Those cells are composed of molecules. Most molecules probably aren't really alive, and yet this DNA molecule, you might be able to argue, is alive, and yet it's composed of atoms that aren't, I would say. Now, this paradox is often leads us to the strange case of the viruses, which a lot of people would say a virus is not alive, even though it has a lot of the properties of a living organism, because it cannot exist without hijacking a larger living system. But if you're going to say that, then I would submit, have to say a human being is not alive, because we cannot exist without a larger system that we completely depend on. Put a human being naked on the moon and see how long they survive. So there's just some kind of fun paradoxes you get to. Now, that's at the small scale. What about at the larger scale? We've been talking about the origin of living organisms, but there are properties of living systems that are larger than organisms. And there's some ideas about this. There's living systems theory, and Hal Morowitz in the early 80s wrote some interesting papers about what he called the what did he call it? Basically the biological properties of ecosystems, where he submitted that life might be better defined on that level rather than on the individual organism level. And this then goes all the way up to what you've heard of as the Gaia hypothesis, a much abused and much maligned idea, which I think is also very profoundly important, the idea that a planetary biosphere has some properties similar to those of living systems. So in this graphic, you see this sort of bog where there are obviously living organisms, these birds and fish and things, but then there are these, for instance, the dead log is dead, but some of these other organisms are completely dependent upon it for their life. So in some larger sense, that decaying log is part of this living entity, this biosphere of the bog. And of course, you have the case of the coral reefs, where the, quote, dead parts form the skeletal structure that the, quote, living parts are completely dependent upon. And so the whole thing has a life that, in a sense, is larger than the organisms. And then you take that to the larger scale, this picture on the lower right, reefs completely remake landscapes. And so there's the boundary between living and dead, even on that geographic landscape scale, is not completely clear. And then you take that all the way up to the planetary level, and again, you're left with this Gaia picture. And the Gaia hypothesis, by the way, as I said, it's been maligned as the Earth is alive, the Earth is a living organism in this sort of New Agey way, which is nice and poetic. I kind of like it. But there's actually a more scientifically useful way of thinking about it, which is that the totality of the quote living and quote non-living parts of the Earth function in a way so as to achieve homeostasis that tend to emphasize certain negative feedbacks that keep the whole ball, as it were, rolling in a way that keeps it in that range of physical conditions that are conducive to the furtherance of life. Just as in your own body, there's homeostasis going on with your temperature and the pH of your blood and all these things. And it gives us a slightly different picture of evolution. It's actually a modification of Darwinism, because you realize that it's not the case where the environment is just changing and life is just adapting to it. But on a planetary scale, life changes the environment. And so therefore it's a feedback and a dance between the two that can lead a planet to a very different state than it would be if it were not, in a certain sense, taken over by life. And as my colleague Colin Goldblatt put this, the defining characteristic of Earth is planetary scale life. And Earth teaches us that habitability and inhabitants are inseparable. In other words, if you compare Earth to other planets, which I'm going to do a little bit more in a minute, it jumps out at you how the life of Earth dominates so many of its physical characteristics, not just the composition of the atmosphere, as I mentioned, but the mineral balance of the planet, more than half of the minerals on Earth exist because of living systems. The composition of the ocean, the climate, even now some people think the composition of Earth's interior, which affects the material properties and convection of the planet more speculatively, and the heat flow of the planet, are influenced by and potentially controlled to some extent by life. So Earth is a planet where habitability and inhabitants have become inseparable, and we're not really sure how far that goes back, but when we compare Earth to the neighbors, Venus and Mars, it's a stark difference. Now, one other way to think about life I just want to mention. This comes from the field of non-equilibrium thermodynamics, and there's something called a dissipative structure that you've all seen because you've seen dust devils and at least films of tornadoes. Hopefully you've not seen one really up close. But you've also seen whirlpools and vortices, and not just on Earth, on the upper right here, this is on Venus, this polar vortex. And a dissipative structure is a structure that arises spontaneously when you have the right kind of flow of matter and energy, and matter organizes itself in a way to facilitate that flow. It's sort of spontaneous order that arises from flow. And you look at these standing waves in this stream on the bottom graphic here, and you can, if you want, relate that to yourself and think, what am I? Am I the atoms and molecules that right now are part of me, but they're not going to be part of me in the future, and they weren't always part of me, and yet I'm still me? So there's a sense in which a standing wave, which is a structure that persists even as the matter flows through it, is an interesting model for what a life form is. And if you think of life as that, as something that arises from flows of matter and energy, structures that evolve from that, then again you can think of the Earth and its biosphere as the most complex dissipative structure that we know. And another example of such a structure that you're familiar with is a fire. And this also has captures another quality that I want to mention because I think it might be important in how we think about life on planets. And that is, think about when you build a campfire and you're trying to get it started. And at first it's just sparks and it's really hard to get it going. And you have to stay there and keep blowing on it, and it does, you've got sparks and you've got your fuel, but it's like disorganized and it's a pain. But then you get it to a point where it's going enough and the coals are hot and it's creating its own convection pattern by sucking in air and the hot air rising, and then it's fueling itself by pulling in oxygen, and then it becomes self-sustaining. And it's a self-sustaining dissipative structure which is pulling in its own fuel and taking advantage of the cyclic motion of nutrients through itself. And it's possible that that's what a global biosphere is. And that I want to make the distinction between the origin of life that we've been discussing, which is, it seems to be discussed as a local phenomenon, something that happens one place or one region, but doesn't simultaneously happen all around the planet, and the origin of a global biosphere that is a self-sustaining part of the way a planet is operating, which is clearly what we have here. And when we look around at other planets, which is what I spend my time doing, and think of the properties we're looking for, we're really looking for the latter. I think it's going to be easier to find biospheres or evidence of biospheres than organisms or evidence probably of organisms, although that obviously depends on the case. And it may be that life goes through a stage initially where the origin of life, that's like those sparks that may fizzle and die unless they're fed by the right kind of cyclic flows, but life can get to a point in its existence on a planet that's like that self-sustaining fire. And I'm interested in that potential difference between the origin of life, meaning there's some physical system that is behaving like an organism in the ways we've been discussing, and the origin of a global biosphere that might be a property that a planet takes on. In other words, in a sense, maybe life is not just something that happens on a planet, but something that happens to a planet, or something that a planet becomes. So this leads me to the musical question, can a planet be alive? And it's something I've thought about a lot, especially with reference to comparative planetology, which is really my day job. And there's a growing field among those who do study planets, where what we really are interested in is comparing the life stories and environments of planets to try to understand them not just as points in time, but as pathways, as stories that collectively illustrate properties about what can happen to planets. And one thing that can happen to planets, clearly, because it has here, is becoming alive. So how does this question of whether a planet can be alive, how is that illustrated, or what light can we shed on that by looking around at the neighbors? Well, we look at Mars, and ever since 1971, we've known that Mars is a place that seems to have been much more Earth-like. I say 71 because that's when Mariner 9, the first orbiter, got to Mars and really started it. We saw that it was, the older parts of Mars were covered by dried up riverbeds. And as we've explored Mars in depth since then, we've learned much more that indicates that Mars, when it was young, was much more Earth-like. And now we have this wonderful rover Curiosity that's slowly crawling across this lake bed. Turns out it is a lake bed, as we thought from orbit, of Gale Crater, and starting to climb up this mountain, Mount Sharp, and finding copious evidence of a more watery, more wet, more benign in terms of climate, more Earth-like past. And just one bit of evidence you can see in this image here, this rounded cobble. These are river rocks. You could tell when you look at them up close and you compare them to rocks on Earth. These are rocks. This is a place where water has flowed. And I won't go into more detail about Mars. Obviously, one can talk a lot about this, but the punchline is that Mars, when it was younger, was a more Earth-like place in precisely those qualities that we think would be conducive to an origin of life, as we are, imperfectly but increasingly seem to understand the requirements for that. And there's some problems with Mars. The climate models don't quite work to make it warm when it was young, but the geology tells us it was watery, so there's still something we're missing about Mars, but things are pointing in that direction. Now, when we go to the other neighbor, Venus, as you know, now Venus is hell on the surface. It's far too hot for our kind of life. There's almost no water. It's not a place you would want to live today, but in the past, our understanding of Venus is more clouded, literally and metaphorically, than our understanding of Mars. But what we have learned so far points us to Venus being, in the past, also a much more Earth-like place. And we have some designs for new missions, which we're hoping to fly in the near future, which are really designed to take the measurements that will help us pin down whether that's really true about Venus. But as far as we can tell, if I had to draw you a picture of the earliest environment of Venus, or not quite, the second environment of Venus after it was a fiery pit of impacts, as all the planets started out, but then once that quieted down, I would say it would be sort of like this picture. And you notice this picture is kind of murky because our understanding is murky, but basically this is what Venus and Mars probably both looked like around the time we think the origin of life happened on Earth. They were water worlds, and they probably had black smokers and things like that because the heat flow was much higher then, and things point towards origins that were conducive to life on these planets. And this makes me think that the lesson, the punchline of comparative planetology in our region of space, and increasingly farther afield, is that rocky planets have similar origins in early environments. That it's not uncommon for rocky planets to have wet conditions, not just wet, but in places where there are chemical flows and interactions with geothermal heat, and they all certainly had organic molecules, because we're learning more and more that organic molecules are basically everywhere, falling from the sky and being synthesized. And so I would say that from what we know about the origin of life and its requirements, which, as you've heard, are still far from perfect knowledge, but from what we know, and from what we know about the early environments of these planets, there should have been life on all three of them. Not only do I say that because it seems like conditions were right on those planets, but even if it was something more rare, another thing we've learned is that the planets were all exchanging materials back then. There were bits getting blasted off of one and landing on the other, and microbes being the hardy beasts that they are, life would have been transported from one to another. So even if an origin of life is rare, you might not need to have it indigenous to a planet. If it happened on one of the neighbors, it could have easily spread. So similar origins in early environments, and therefore what is rare is not perhaps the conditions for the origin of life, but the persistence of the conditions to maintain life over cosmological timescales, that is, over billions of years, the ages of planets. And that leads me back to this question, did the presence of a global biosphere on Earth help with that persistence? So maybe we're not just completely lucky. Maybe life itself had a hand in keeping Earth habitable. Now, the very first environment of all these planets, as I mentioned, was hellacious. We know they started off very violently with a lot of collisions. And this is the period of time on Earth we call the Hadean, which literally means hellish. That was the first eon of Earth history, lasting up till about 4 billion years ago. And interestingly, I think we can be pretty certain that the Hadean was not a phase unique to Earth, that Venus and Mars had a Hadean around the same time as Earth. Now, did they also have an Archean? That's a really interesting question. So here we have 3 young terrestrial planets, and then something happened to the middle one to lead it to what we've been hearing about. There was an origin of life, and I leave the details to the bio and chemistry parts of astrobiology. But clearly it happened in one place, and I have question marks about whether it happened in these other 2 places. If it didn't, and I think we have to figure out why not. But then, what I wonder is, was there another transition after that to a global biosphere on Earth where you could have had life on all 3 planets, but it could have only persisted on the one planet where the geophysical conditions were perhaps more friendly for that continued set of flows of nutrients and energy on that stable surface environment that allowed a global biosphere to develop and take over and then maintain its own existence. Now, you've all seen the geological time scale, where we have these different ages, and famously, you know, the Jurassic is famous because it's a movie star, and then after that there's the Cretaceous and the Tertiary, and all these are now it's actually the Paleogene, and all these different ages. And over on the right side of this chart are the little, you know, I say little, they last for, you know, a few million years, nothing. These are what we call the epochs. And epochs are not major events in the life of the Earth. They're important to the biota who are alive at that time because they're often marked by extinction events, climate changes, changes in sea level. They're fluctuations that change what can live where, but they don't really affect the planet that much. Far over on the left are the eons. There's only been 4 eons. And the eons are interesting to me as an astrobiologist because I'm interested in the relationship between life and a planet. And each of these eon boundaries, I would suggest, is a time when the character of the planet fundamentally changed, and in particular the relationship between life and the planet fundamentally changed. The Hadean, it was dead because it was just not a place where you would want to live, or anything probably could, because there was not a stable surface, and then you were getting my colleague Kevin Zonley refers to the Hadean as an age of fire and brimstone punctuated with blows to the head. So that's the Hadean. But the Archean is roughly, and geologists and geochemists will throw things at me because I'm going to make some crude statements. But that's basically the boundary between the Hadean and the Archean is the origin of life, more or less. 4 billion years ago, some people put it at 3.8. That's when life, when the planet came alive. Clearly the other planets had a Hadean. Did they have an Archean? That's an interesting question. Now, I think the Proterozoic, which is the next eon, is arguably the time when life took over the planet. It's when we had the rise of oxygen from the cyanobacteria polluting the atmosphere with all this nasty oxygen. They were the original bad actors who, in the search for a new energy source, polluted the entire atmosphere and collapsed the climate, and, just for their own selfish purposes. Anyway, so I think the Proterozoic is when life perhaps took over the planet. The Phanerozoic, which started basically a little over 500 million years ago, is the time when life got complex and animals and plants formed, and life was not just multicellular, and all the forms of life, the macro life we're familiar with and the fossils we're familiar with. There was a seemingly rather abrupt transition, and that's what we call the Phanerozoic. So each of these is sort of a transition in the relationship between life and the planet. And as an astrobiologist, as I said, I'm interested in these because I can imagine, all these little changes on the right side, these epochs are unique to Earth. They're Earth's random evolution. But as you go to this left side, these major transitions, I will submit to you that each one of these is something that astrobiologists could look for on another planet. Okay, I hear you. Sorry, my phone's telling me to hurry up. It's probably good advice. That other planets definitely had a Hadean. If they had an origin of life, we could say they had an Archean. If life took over as it did on Earth, that might be analogous to a Proterozoic. And if life became complex, then that could be the Phanerozoic. So these are all things that astrobiologists talk about looking for on other planets. And so I think these eons map into possibilities for other planets, whereas the smaller boundaries, the epochs and so forth, clearly are just part of the Earth story. So I want to just mention one last transition, which is something is happening to Earth now that's new. If you had been watching Earth over the eons, and you were a patient alien watching Earth from space, you would notice suddenly things had changed. The Earth lit up, and the atmosphere composition and the ocean composition and the ocean acidity is changing, and the land surfaces are changing. These strange linear clouds are streaking through the oceans and across the sky. There's something up on this planet that wasn't up before. And the nature of that transition is basically what I was studying when I was here as the astrobiology chair a few years ago. And it's something that people have been calling the Anthropocene epoch. But I want to submit to you that maybe it's not an epoch. It might be an epoch boundary, but it might also be an eon boundary. One of these major changes. Why would I say that? I think it's a fundamental change in the relationship between life and the planet, because cognitive processes, making things, tool use, are changing the planet in profound ways. And life has changed the planet many times in the past, but cognitive processes being involved in the functioning of the planet, that's something new and very strange. And if it persists, I think arguably as significant even as the origin of life, and therefore could be an eon boundary. We won't know for hundreds of millions of years. This is, my idea cannot be disproven even by the remote descendants of anyone alive now, so I feel pretty confident in making it. But anyways, so here's dead planets, here's planets with the origin of life, here's planets where some of them have gone through a transition to a global biosphere, and just maybe there's a class of planets out there where this transition to cognitive function as a part, and technology as a part of the way the planet functions has become something long term. And there's some fascinating arguments that I don't have time to go into now about whether that's possible, whether quote, intelligence is something that always will limit itself by giving itself the power to wipe itself out, or could we be like the dinosaurs that had a space program and therefore survived the extinction by pushing the asteroid out of the way? There are ways in which you can imagine technology leads to longevity. And that, by the way, I'm not going to talk about that more now, but this allows me to make a plug for the book, Earth in Human Hands, which is in fact the project I was working on when I was here as the astrobiology chair. And I just wanted to show it off, not just because I want to make a plug for it, but because my good colleagues here at the Kluge Center, I think they had a sneaking suspicion that I wasn't really doing anything, because why did this take so long? So I want to say, aha, see, it's a book. Earth in Human Hands. Thank you. By the way, it's being published this December. It's being printed now. This is an advanced galley. And for those of you in town, I'm having a launch party at Busboys and Poets December 7th. Please come join us. And getting back, and I'm ending now, but getting back quickly to this geologic time scale with all these transitions I talked about, I would submit that this new boundary we're going through could be an eon boundary, and I propose the name Sapiazoic for what we're entering, the phase of Earth that is characterized by wisdom. Now, that seems sort of arrogant. In fact, it was arrogant of Linnaeus to name us Homo sapiens, which means wise ape, because if you look at our behavior now, we're not doing so well. But my point is that the only way it would become an eon is if we get our act together and persist. And so it's an aspirational title. If we don't get our act together, then it's not going to be the Sapiazoic. It is going to be just a little blip of an Anthropocene. But I think our history, our long history, suggests that we are a species that, when faced with extinction, which we have been before, reinvents itself and uses its innate gifts for communication and creativity and collaboration to imagine new futures and create them. And so we certainly have a rough century ahead of us, but when I take this big picture view, personally, I'm not at all devoid of hope. And finally, coming back with my last slide to astrobiology, the potential for Sapiazoic transitions, I think, is one that we also at least have to consider on other planets, along with these other transitions that I mentioned. And if that is the case, then there's another way to think about finding intelligent life out there. We don't have to assume they're sending signals to us, which is kind of a weird assumption. Like, why should they, right? I mean, there's one kind of alien life you could imagine that might want to. There are all kinds of alien life you could imagine that would have no interest, just like you have no interest in discussing philosophy with a frog. Maybe you do, but what's cool about if there are planets out there where this transition has happened, then we can find them even if they're not trying to talk to us. It may be that there are three types of exoplanets: dead ones, living ones, and sapient ones. And I'll stop there. Thank you.
Yeah. Oh, do you want to do questions now, or why don't we do them both afterwards? That was an amazing talk, and you know, he's too humble to mention this, but he has a new book coming out in December. Earth in Human Hands. Our next speaker is another astrobiologist and a historian. And he was the longtime chief historian at NASA. Before that, he spent 20 years at the US Naval Observatory, and he probably knows more about the development of exobiology as a field than anybody else out there. He's going to talk about that, among other things. One of the things he's going to speak about is something that really caught my eye, and that is the idea of panspermia, the idea that life on Earth may have originated elsewhere. So he's going to become the second speaker after Steve Benner to mention panspermia. And I think 30 years ago, if you were at a conference on the origin of life and two people had brought up panspermia, the next speaker would have been in a sailor suit and trying to sell you Dianetics. But now it has once again become a mainstream thing, and I'm not advocating it or arguing against it, but I think it's fascinating because it illustrates that science doesn't really travel in that straight diagonal line that I think most of us imagine when we think about science, this idea that we're going from ignorance into illumination, and it's just this easy, clear path. I think sometimes science zigzags, and panspermia is one of those ideas that a century ago, or in the late 19th century, it would have been a widely accepted idea, and was two of the proponents were two of the most important scientists of that time, Lord Kelvin and Savant Arrhenius. And it was so widespread because scientists had a hard time reconciling Darwinian evolution with what they thought at that time was an Earth that was only 100 million or even tens of millions of years old. So panspermia fell into ill repute, but it's now come back in interested in hearing more about that. So here's Steve and Dick.
Well, thanks a lot, Bill. And as with David and Nathaniel, of course, I have to say how great it is to be back at the Kluge Center here at the Library of Congress, where I spent a fabulous year a couple of years ago, a very enjoyable year. So thanks, Nathaniel, for having me back. And also thanks to Jim Green and Mary Wojtek over at NASA headquarters, who fund this great Blumberg Chair in Astrobiology, which has the purpose of looking at the humanistic aspects of astrobiology. And I was very pleased to see in the latest astrobiology strategy document that they have an appendix beyond the natural sciences about the role of the humanism or humanities and social sciences. So that subject is coming into its own in astrobiology. I think it's really an important role for the humanities and social sciences to examine the impacts of astrobiology, just as it has been for the Human Genome Project. These days, I think it's all part of the larger need to relate science to society, and which I think especially we need to do these days. Well, when I proposed this title for my talk, Nathaniel said, "You can't do that in 20 minutes," and he's right, of course. If I were going to do this in an hour-long lecture, I would do something like this. With more time, I would so systematically lay out some of the metaphysical and ontological and epistemological issues in the origins of life studies. I would clarify its central concepts, such as the meaning, what is life, as we've been hearing about. I would talk about some of the methodological issues and how they limit our approaches to the problem, in the same way that Martin Harwood has recently written a book about arguing that what we know about the universe really is shaped by the tools that we have for astronomy. And I think the same is true about origins of life studies. And I would examine the societal impact, but I'm not going to be able to do all that, so let me focus on just 2 or 3 of these briefly. Issues that really popped out at me when I wrote the history of the extraterrestrial life debate in my book, The Biological Universe. And I think they're just as relevant now as they were then, because these are general philosophical issues. It's always been interesting to me also, I want to say that one of the earliest goals of the space program was exobiology, as it was called in those days, the search for life in the universe, thanks to pioneers like Joshua Lederberg and Jerry Soffin and Carl Sagan, many, many others. And I think you could easily argue that the search for life in the universe has been an important driver of the space program, certainly when it comes to the exploration of Mars. Some of the ocean worlds that we're now talking about continue to be drivers of the entire space program. Everybody, when I was at NASA, you go around giving talks, everybody wants to know about life on other worlds. So astrobiology really is at the forefront, not only in science, but also in the public interest, I would say. So let me begin with a conceptual issue that is really at the heart of everything we've heard today. If we were going to search for life on Mars, we had to have some idea what to search for. So the first of the philosophical issues was raised almost immediately. That is, what is life? That's the question that's been in the background of all the papers we've heard today. Many people have tried to answer that question. You'll be happy to hear that I'm not going to try to answer that question today. After all, my background is more in astronomy than it is biology, but I do want to talk about the controversy over the question, because it's similar to some of the questions we have in astronomy. And in fact, all of these historical and philosophical issues that you see here are ones that you find in astronomy also. Someone recently quipped that life is what's left over after you eliminate everything that's not alive. Somehow I don't think that's really very helpful, but the question is an old one. It's contemplated by biologists and biochemists, physicists like Schrödinger over several centuries. That history reads like a mirror of each period when the question was asked, as biologists tried to determine the physical basis for life with attention turning successively to protoplasm, the protein enzyme, the virus, the gene, and the cell. And by 1937 already, the British biologist Norman Peary was arguing that the terms life and living were really meaningless, that the transition from non-living to living was comparable to the gradual transition from green to yellow in the spectrum. It's like seeing a rainbow. You know, when do you transition from one to the other? Or like going from acid to alkaline in chemistry, except that life itself could not be defined in terms of only one variable. Well, today the debate about the origins of life is at the level of the molecular assembly of life. We often see this NASA definition of life as a self-sustaining chemical system capable of Darwinian evolution. But I think there's a consensus that no single definition of life is totally satisfactory. Some philosophers and scientists like Carol Cleland and Chris Chiba say that they've argued repeatedly, beginning with a series of papers in 2002, that all attempts to define life are fundamentally misguided in the absence of a general theory of living systems, which of course we don't have. Other philosophers such as Kelly Smith call this stance definitional pessimism and argue that you don't need to have a universal definition of life to have a working definition for any given circumstance. In other words, there has to be a balance between definitional pessimism and pragmatism. And I really tend to come down on that side, on Kelly Smith's side, for several reasons. First of all, because we really can't help ourselves from defining life, can we? Just as we can't help ourselves from defining a lot of other things like, say, planet, to take a random example, from astronomy. Secondly, institutions like NASA, of course, need an operational definition of life if they're going to search for it. The latest astrobiology strategy document specifically says that definitions of life and function and evidence, those kinds of things shape our research, and therefore we need them, even though we don't need to obsess over them and they need to be elastic. We need to be able to adjust them. In astronomy, we think of the controversy surrounding the question, is Pluto a planet? You've seen the amazing images coming from the New Horizons mission, which David is also writing a book about. But of course, whether or not Pluto is a planet depends on your definition. The International Astronomical Union 10 years ago, last month, decided that the answer was no, that Pluto was not a planet, based on a rather arbitrary set of conditions, I think some people would say. It was a compromise among the astronomical communities that defined Pluto as a dwarf planet, and then declared that a dwarf planet was not a planet. Well, I voted for the dwarf planet part, but I've always thought that a dwarf planet should be a class of planet, but it's not by definition. The point is, though, that it was defined in a way that reflected these different astronomical communities, even though it disappointed some scientists like Alan Stern, who's the PI for the New Horizons mission, not to mention a lot of other school kids who were disappointed. It was an interesting cultural phenomenon, really. But you'll notice that arguments over definition of a planet didn't keep New Horizons from having a spectacular mission, right? Alan likes to point out that Pluto doesn't care if it's a planet or a dwarf planet, so we go and study it anyway. And the same is true of definitional problems with things like species. A common definition of species is organisms that can interbreed, belong to the same species. Well, we now know that Homo sapiens and Neanderthal interbred, right? So most of us are 1 to 3% Neanderthal. So instead of throwing out the concept of species, we expand or adjust the definition. And the same is also true of intelligence. David mentioned intelligence, which the SETI people like to skirt by talking about the search for extraterrestrial technology, not intelligence. Then they don't have to define intelligence. And I remember right here at the Library of Congress a few years ago asking the philosopher John Searle about the concept of intelligence. He said, forget intelligence, the big question is consciousness. And of course, nobody knows how to define consciousness either, right? There's no consensus definition. So we all settle for operational definitions that apply to the specific task at hand. So people like Carol Cleland and philosophers, I think, have a good point when they say that we can't have a universal definition of life in the absence of a living systems theory. I certainly agree with that, but we do need operational definitions. Now, of course, those operational definitions can get you into a lot of trouble, especially if you choose the wrong definition when you go off searching for, say, life on Mars. And that was the case with the Viking biology experiments, all of which relied on a definition of life based on metabolism. Gil Levin, one of the principal investigators, still believes that he found life on Mars, a claim that's no longer so much completely dismissed as it used to be, given what we now know about the surface chemistry of Mars. For many years, that result was trumped by what's called the GCMS, the gas chromatograph mass spectrometer experiment, because it showed that there were no organic molecules on Mars at those 2 landing sites where the Viking Landers landed. So if you have no organic molecules, you can't have life, right? So that sort of wipes out all the experiments on metabolism. In effect, a biochemical definition of life trumped all the other metabolic experiments until we found out more about the role of perchlorates on the surface of Mars. So the lesson of Viking seems to be that experiments should be designed with multiple definitions of life in mind. Now, the best way to define life, of course, would be to actually find some on Mars or Europa or Enceladus, some of these other places, and compare it to Earth. In that case, if it was truly a second genesis, we might have the beginnings of a universal biology, similar to a universal physics that we think we have now. And that's the second issue I want to address, the aspirations for universality, by which I mean 2 things. Is there a universal biology as there is a universal physics? And is life universal? In other words, is it spread throughout the universe? So in this respect, I think there's no doubt that the space program really catalyzed aspirations for universality in both of these ways. Implicitly or explicitly, those at the intersection of exobiology and origins of life expressed interest in the desire for a universal biology, one that might be more general than terrestrial life. In the Soviet Union, Oparin called exobiology and the origins of life the inseparable connection. And Stanley Miller did the same thing. And here we saw the Yuri Miller experiment this morning. Some of you may notice that I have 1952, whereas I forget who it was who showed it this morning, had 1953. I think that's the difference. This is an interesting thing about when is a discovery made. Is it made when the experiment is done, or is it made when the publication comes out? Well, in this case, the experiment was done in 52, but it's always cited as 53 because that's when the public. That's an interesting thing in science. I've done a whole book on that. Anyway, both of these scientists said that exobiology and origins of life are the inseparable connection. Origins of life studies quickly became a central focus of exobiology, bringing into the field scientists such as Melvin Kelvin. I once interviewed Melvin Kelvin in his office at Berkeley, best known for his Nobel Prize in having to do with photosynthesis. But Kelvin said in his mind there was no question about the Darwinian behavior of molecules, and if that were true, that meant it must be true in the entire universe. His student, Cyril Pranamparuma, said basically the same thing. If we can understand how it began here, we'll know something about how it began and if it began out there, and if it's repeated in the staggering number of planetary systems in our galaxy, or in our universe even. Now, that was written in 1972 when there were no other solar systems known aside from our own, right? Of course, now we know that they're everywhere. So in short, the space program, my point is the space program catalyzed the integration of origin of life and extraterrestrial life studies as theories and experiments that were previously viewed just in the context of life's beginning on Earth were increasingly seen in an extraterrestrial context, integrating these 2 fields of study. Now, these conclusions about universality of life really hide a deep metaphysical preconception, and that is the question of chance and necessity in the origin of life. I think it's a real tribute to the scientists involved that they recognize their preconceptions. In fact, the philosophical question that dominated the problem of origin of life beyond Earth was exactly that. What was the role of chance and necessity in the formation of life? After all, on that question hinged the whole enterprise of exobiology, what we now call astrobiology. Because if life was just a chance occurrence and was very rare, then it might never happen again, no matter how big the universe was or how much time you had. In my mind, the two prototypes for the debate over chance and necessity are Jacques Monod and Christian de Duve. Here you see Jacques Monod, a French biologist. Monod and de Duve both are Nobel Prize winners. Monod was awarded the Nobel Prize in 1965 for explaining the genetic regulation of protein synthesis in cells. And he drew on the latest results in molecular biology to illustrate how chance predominated in all aspects of life's development. He wrote a classic volume called Chance and Necessity, written in 1971. And he famously wrote this phrase, which you often see quoted: "The universe was not pregnant with life, nor the biosphere with man. Our number just came up in a Monte Carlo game." So he came to that view because of what he called the revelation and the disappointment that the sequences composing the insulin protein showed no general law of assembly, only the blind workings of chance. Many scientists since that time have agreed with him, including some astronomers like Fred Hoyle, who famously argued that the origin of life by chance was about as likely as a 747 aircraft being assembled spontaneously from a junkyard. It's a pretty good image. He thought it was vastly more probable that life had been assembled by a cosmic intelligence. But before the religious people could get too excited, he emphasized that in his opinion it was not a supernatural intelligence. But that's another subject. And in his book, Advocating Panspermia, Francis Crick tended to agree that life could not have risen by chance here on Earth. Well, a quarter century after that, here's Christian de Duve, who just died last year. He wrote a book called Vital Dust, Life as a Cosmic Imperative. And he argued just the opposite from his Nobel Prize French colleague, Monod. And he is a very well-known biochemist also, best known for his discoveries related to the structure and function of organization of a cell. And he was most impressed with the organic molecules then being discovered in space. So it's interesting how these two came to their ideas about chance and necessity. It was based on things that were currently happening, sometimes on their own research. So he wrote, as you see here, that in the organic cloud, and here he's talking about these organic molecules being discovered in space, which we now know exist all over in interstellar molecular clouds, that they were everywhere, and the conclusion seemed to him inescapable, that where the conditions are similar to those that prevail on our planet, that there would be life. And he went so far as to say that those who claim that it's highly improbable just haven't looked closely enough at the chemical realities. So there you have two, pretty smart guys, both Nobel Prize winners, with totally different points of view on that. Okay, I think it's one of the hallmarks of exobiology and now astrobiology that its practitioners place their faith more in necessity than in chance, or at least the high probability of the origin of life under proper conditions. It was their most basic metaphysical presupposition. Otherwise, they wouldn't waste their time searching for life, right? If you don't think it's very likely, you're not going to put much time into it. I happen to agree that this is a good presupposition, partly because, as we've heard, life seems to have arisen so quickly on the Earth. We've heard this morning several times about the discoveries just announced last week about the life 3.7 billion years old, just after the Hadean period that David was talking about, the heavy bombardment of the Earth. Those were fossilized stromatolites, like the ones that Steve passed around this morning. But these were from 3.7 billion years ago, stromatolites from the Ishura Rocks, southwest coast of Greenland. So that's less than 1 billion years after the Earth was formed. You already had life beginning. And that seems to me also to argue for a role for panspermia, maybe, that the spreading of life throughout the universe, or at least giving life a head start by spreading complex organic molecules, which we know are ubiquitous in these interstellar molecular clouds that so impressed Christian de Duve. Beyond life's rapid origin on Earth, the idea of necessity seems to me also to be reinforced by the fact that the physical laws, we know now that the physical laws of nature are universal, and that what happened here ought to happen there. That certainly is a presupposition, but it's a recognized presupposition that seems to work pretty well. It certainly worked for the planets, right? I can remember prior to 1995, people saying, we don't know about any other planets outside of our solar system, and we didn't. But with this presupposition, a lot of people said the physical laws of nature are universal. What happens here happens there. Lo and behold, there they are. Not only they're virtually everywhere, even around, as we've heard recently, around red dwarf stars. In fact, which is what Proxima Centauri is, the closest star to us, has planets. Now, of course, they don't have life. Most of those don't have life, but some of them are in their habitable zones and could have life. That's a metaphysical presupposition, and with the discovery of extremophiles that we've heard about this morning in the form of hydrothermal vents and deep underground, we know now that proper conditions are much broader than we thought in the past. And we also know that the idea of a habitable zone has been expanded. Who would have thought that the moons of Jupiter and Saturn were in a habitable zone? Well, they are, right? They're way out there, don't get much solar light, but they do have tidal heating, which allows them to have liquid oceans, which means life could exist. That's not to say that it will be like ours, far from it. There'll be diversity, just as there is diversity in the planets that we're finding now. They're not all like ours by any means, the gas giants and orbiting near to their stars and that sort of thing. So there will be a lot of diversity, I would predict. But this idea of universal laws producing similar outcomes with diversity has been proven over and over again. It remains a presupposition, it's true, but I think it's a good one. Some presuppositions are better than others. So that's the presupposition, the metaphysical presupposition behind astrobiology. That's one of them. Well, that gives rise to even deeper metaphysical questions. Why is the universe biofriendly to start with? Do we just happen to live in a universe where the constants of nature are such that the galaxies, planets, and stars and life can form? We couldn't have life, we don't think, unless we had the planets and the stars. But the conditions of the universe have to be right. The constants, physical constants, have to be right for those things to happen. Is life in some way one of the fundamental entities of the universe? Here you get into what some people call the anthropic principle, which I would rather call the biocentric principle. And in talking about that, people ask, is there some deep connection between life and the very structure of the universe? Questions like this really lend all the more importance, I think, to astrobiology, because astrobiology is going to determine just how abundant life is in the universe and whether it is a basic principle or whether we are a fluke. Some argue that the biological universe may not be the result, but the cause of the physical universe, which is a pretty strong statement. But maybe life is more fundamental than we've ever realized. Here's a quote from Freeman Dyson, who's known for some wild ideas, it's true, but also a very well-known physicist, saying that it almost seems as if the universe knew we were coming, and he predicts the bright prospects for a future-oriented science that would look to the future rather than the past, and would mean life and intelligence on an equal footing with general relativity as factors influencing the evolution of the universe. Okay? So we've come quite a long way from the origins of life we were talking about this morning, but I think this points out that origins of life could not have occurred unless the universe was biofriendly. So this takes you from one end of the argument to the other. So I think my time is up, but you'll see that I have, after all, touched on quite a few of these, just in a cursory way of these issues. except for the last one, and I just want to say a word or two about that. In the end, we still don't know whether or not life is abundant in the universe. That remains perhaps, I would say, the greatest question in science and in the history of science. But if there is life out there, I think it's prudent that we prepare for that discovery, which in the long term could change our worldviews in the same way that we were changed by the Copernican and the Darwinian systems. And I say that even if the universe is only full of microbes, which a lot of people think might be the case. After all, if you look at here on Earth, it took us a long time to get from microbes to intelligent life, right? So the challenge of the societal impact of astrobiology is a very large topic, and that's what I spent my year at the Library of Congress studying. And if you want to know more about that, there's the book that I edited on this subject based on the Blumberg symposium that we had 2 years ago. This is published by Cambridge University Press, so you might think it's out of reach in terms of the price, but actually it's not. If you go onto Amazon right now, you can get it for $2.98. So that's a bargain. And I think you'll find it stimulating on a wide variety of issues, not just origins of life, but a lot of these other societal issues beyond. It's one of the great things about astrobiology, that you can talk about not just the chemistry and the physics and the astronomy, but also the humanities, the social sciences, theology, all kinds of things when you talk about societal impact. So thank you. I think I'll stop there.
After you. Do you guys want to sit?
Yeah, I guess. Definitely.
And we'll move quickly into questions because you've heard two wonderful talks, and I'm sure we're going to have a lot. Anybody? Right there.
Yeah, I'm good. Oh, thanks.
I think he's bringing you a microphone.
Question is for Dr. Grinspoon, and I was really intrigued by your concept of the cognitive intelligence for not only Earth, but the galaxy. And would you please develop that a little more? Does this mean that we create life through intelligence?
Not necessarily, although it's interesting. One twist of this transition, if there is a transition towards cognitive life being part of the planet, which I would argue there could be. One interesting twist on that I didn't have a chance to mention is some of the work we've been hearing about here gives us the potential to also become the engineers of evolution, and that's another way in which a Sapiezoic eon on a planet could be defined, because you could argue that natural selection is no longer full stop. That even the Darwinian evolution that's going on the planet now is in an environment, a global environment that's perturbed by the cognitive, for better or worse, the technological and industrial activities of humanity. Now that's always true that evolution of species have affected the evolution of other species, but I would maintain there's a fundamentally different kind of process going on. So what I was talking about specifically was just looking at the mechanisms of change on the planet, and what I was doing when I was here as the chair was trying to look from a planetological point of view at this transition that's happening to Earth now, and try to define that in a way that's not just human beings are doing this, but is there a more abstract way that we could possibly map into planetary history that might obtain on other planets as well, and that's where I focused on this. You know, you could argue that cognitive, that nervous systems are something that will evolve on other planets if life evolves. I won't go into it now, but there's a good argument for that. And therefore, even though intelligence is hard to define, you could argue that something like human type intelligence and some of the salient aspects would evolve elsewhere, and technology. And therefore, if it got to the point where it was affecting the evolution of its planet, which I think it has here, then that might be a Sapiezoic elsewhere in a sort of not human-centered but more abstract sense.
This is for Steve. I'm not an astrobiologist, so I'm an historian. And I want to phrase two questions. Is there a slight possibility that we approach this question from death? In other words, we take death as an opposite of life and see that opens up a bigger discussion.
That opens up what?
A bigger discussion. If we approach life from death, seeing death maybe as an opposition, and the extent to which that expands some of these notions. I'm just trying it. I don't have any answer.
That sounds like the idea of the absence of life being used to describe life.
Yeah.
So in terms of that definition of life, I don't think it's an exclusive terrain of astrobiologists. I think it's a fundamental question that we all have to face, even outside of the academy, in which mythologies, religion, spirituality are going to create their own contestations in which...
Well, so how is that a challenge for astrobiology? The fact that you are sharing a landscape that is a metaphysical landscape, not astrobiology, but origin of life, and in talking about what is life. I mean,
well, I think it goes to the question of our place in the universe. The question about the death, my view on that would be, I don't see how it helps that much, because if death is the absence of life and you don't know what life is, I don't see how that helps. Unless you're talking about it in a more metaphysical sort of a way. But in general, and not in a scientific way, but in general, I would say that you're talking about an even broader definition of life as the life that we live, right? Not the life that's originated, the origins of life. So I think astrobiology helps us in terms of figuring out what our place is in the universe, because it's a very different universe. If we are the only life on this, in our solar system, and even in the entire universe, we know that in our own solar system that there's, we're I would say almost certainly the only intelligent life. But if we're the only life in the galaxy, or if it's extremely rare, that gives us a different sort of view on life in general, as you said, a sort of more metaphysical, spiritual phenomenon than if life is common. We'll have to, if intelligent life out there is common, we have to share the universe with that intelligence and learn how to interact with it. Whereas if we are the only intelligence in the universe, then the universe is, I wouldn't want to put it in a way of we should exploit the universe then, but the universe is a very different place, and I think it puts more emphasis on our stewardship of this planet and any other planets that we go to, and all the ethical questions that arise if we are the only life. Either way, it's a very sobering thought. There'll be lots of ethical questions too if there's lots of intelligence out there, or even if there are microbes out there. All kinds of ethical questions about, how do you treat an alien microbe? Questions about our forward contamination and back contamination. Of course, NASA has robust programs to deal with that in the very short term, but they have nothing to do with it in the longer term about what you do about microbes if you discover them. Yep.
And David,
yeah, just quickly, I would add that there might actually be a pragmatic interpretation of your question for astrobiology. I've actually thought about, does it make sense to think of the search for death in the universe. We talk about the search for life in the universe. And it might, in one way, which is, of course, you can't have life without death, I think, in our understanding. And if you look at the chances of life existing or having existed on other worlds in the universe, and you do the math, there are a lot of solutions that suggest there are probably a lot more planets where there was life once than there are planets where there is life right now. So if we thought about how to identify planets where life had died out and not just where it exists now, that would be maybe one way to interpret the search for death in the universe. And it might actually be something that gives us a lot more to search for.
Might be more difficult than the search for life.
Ladies first. I'll get you next. Okay.
Doesn't this get us into the question of existence, of consciousness without body, molecules? And is that life? And where is that connection?
You mean his idea of planetary intelligence?
I'm talking about consciousness. As we know it, it exists within our lives, our molecular structure. But
that's a tough one. As Steve mentioned, I think you were quoting John Searle.
Yeah, Searle.
Forget intelligence, so he wants to look for consciousness. I mean, the fact is we don't know what it is. We sense, we experience it, we have some ideas that we might be able to induce it in computers. So is it something we can talk about searching for? I mean, I skirted that when I said intelligence. I put it in quotes because these are problematical terms if you really want to get into it. Is it something that could exist beyond a physical body? I mean, as Bones might say on Star Trek, I'm a doctor, damn it, not a a philosopher or a theologian. I haven't the foggiest.
or Fred Hoyle's black cloud, which was probably conscious.
Right.
It could communicate.
Yeah.
Consciousness existing on other planets without bodies or lives or molecules as we know them, just consciousness.
Well, that's thinking out of the box.
Would that be life?
And right here.
Thank you. I want to ask David about the Large Synoptic Telescope and whether or not we could imagine elsewhere in the galaxy a more advanced version of this telescope, and whether or not they could detect life in this solar system.
Absolutely. We're just at the beginning of the exoplanet revolution where we can know something about the planets in other solar systems. And just the fact that we know there are planets on other solar systems, that alone is a revolutionary bit of information that we didn't have, when I think anybody in this room was born. It's brand new. Now we're at the stage where we're starting to learn something about those planets, but we're in an early stage of that, and we can imagine massive space telescopes with massive occultation structures that allow us to, do direct imaging of other planets. And yeah, I think there are quite possibly civilizations out there that have telescopes that can see things like the lights on our planet at night and can, with spectrometers, notice that there are changes happening in our atmosphere. I wouldn't put it past them.
Right there.
Today we discussed the chemistry of life, biology of life, and I want to comment on astrophysics of life. So we live next to an active star called the Sun, and the Sun causes the profound effects on our planet. And if we want to find life, we want to find life through the interaction of solar effects, of solar events, solar flares, coronal mass ejections, energetic particle events with the atmosphere, with the chemicals produced by life in the atmosphere. So, and instead of probably looking for life itself, which is represented by pretty complex molecules, we want to look for the signatures of pre-life, or prebiotic chemistry that we talked about, without which life is impossible. So might be it's our best bet to go after the strongest signal possible to look for to use our telescopes intelligently to find those environments that have a pretty strong signal with the nearby host stars that interact with those atmospheres that are pregnant with life, and basically to go after pregnancy rather than for life.
Yeah, that's a burgeoning field in astrobiology. It's the next big thing, I would say, what they call biosignatures. Looking for, you know, the James Webb Space Telescope, the successor, sort of the successor to Hubble, will be able to look at the atmospheres of planets and see if they have oxygen or methane or some of these other things that might be indication of life. But you're right also in the sense that astrobiology differs from exobiology. When it was founded, was almost entirely origins of life. Astrobiology deals not just with origins of life, but with the entire system, the entire environment, the sun and you know, and the planets, and how they interact, and what's in equilibrium and what's in disequilibrium, and then this whole idea of biosignatures stems from that too. So that's, you're going to hear a lot more about that in the future.
We have time for just one more question. Yeah.
Thank you. You could sort of, in the discussions you're having about detecting life elsewhere, you could substitute life with life as we know it, you know, based on carbon with DNA. You know, we're going to go look at a planet that would have the signatures of the kind of life that we are. And I'm just wondering how you, do you think that that's a good idea because you really doubt that there could be weird alternatives based on other chemical systems? You know, people have talked about silicon and other things. Or are you comfortable with that because how we don't even know how to look for those other forms of life? Or do you think we should broaden our search for more general principles of life than just saying, oh, look, there's some oxygen that some carbon-based life form gave off?
I want to choose all of the above. We can make the statement that that no one can really imagine, that we can't imagine a life form, say, that's not based on chemistry. And you might say, more specifically, we can't imagine one that's not, that doesn't function in water and use carbon molecules. And I think that's, I mean, we can fantasize about it, but as far as really defining it, what it might be like, I think that's a true statement. But is that a statement about the limitations of our own intellect and imagination, or is it a statement about nature's ability to invent, given the materials at hand in environments that we haven't investigated? So I support the current approach, which is sort of terrestrial-centric in that we are looking for water and we're looking for carbon-based life. And I support it kind of because it's what we know how to look for and it's pragmatic, and kind of because I'm not convinced there is other life that's really very different. But we have to always remember our ignorance and keep our blinders wide open. And that's why I also favor this approach of just looking for atmospheric disequilibrium or looking for anomalous just aspects of planets that seem out of joint, don't seem to be consistent with, quote, natural or, quote, abiotic processes, and prepare ourselves to be surprised. So I think that we're doing the right thing, but we are fooling ourselves if we trust that that's really the only way to search, and we should always be open to the universe throwing us curveballs.
Yeah, I would just agree with that. I think it's a matter of priorities now. You know, resources are limited, and you can always, you know, there are three things: the scaffolding of life, the genetics of life, and the solvents involved in life. You can mix and match all of those things, you know, carbon and silicon and RNA and DNA and protein and water and something else. But I think right now with the resources, it's just a problem of resources, but you have to keep that open mind, you're right.
Okay, thank you. If you had any more questions, there's going to be another Q&A session, is that right? With everybody from the conference.
And I'll ask you guys to stay on stage for just a second. Hi, Jason from the Kluge Center. Just a quick word about what's going to happen next. So our final session of the day is going to be an audience discussion with all of the panelists. So if you did not get a chance to ask a question earlier, or you want to ask more questions, you'll have a chance to engage with all of the panelists. It'll be moderated by Nathaniel Comfort, our astrobiology chair. In the next 10 minutes, we are going to strike this stage and put up a new stage arrangement so that we can ensure all of our panelists have seats. And we are also going to be putting out some food in the back. That food is for the reception at the close of the day. So hold tight, sit through one more Q&A session. You get to enjoy the wine, the cheese, the cookies. So please don't partake of that food now. It'll be open for everyone at 4:30. So we're going to strike the stage, we'll put out the food, and then we'll wrap up with a group Q&A.
Okay, well, throughout the day, we've been delightfully short on time for questions. That's always a good sign for a lively conference, so that's really nice. But now is your chance to ask some of those questions and any further questions that you might have for any of us. And I hope that a lot of this discussion can start to bounce around the different levels of expertise that we've got up here on stage. This, I just want to say, you should feel that what a privilege and treat this is to have this kind of range and quality and caliber of expertise all on one stage. It's just a phenomenon. So I'm just delighted to have you all here. I want to ask, so please, if you have a question, come up to one of the mics that we have here and ask it. And I would only ask that you try to keep your questions concise and so that we have enough time for everybody to ask theirs. So, you know, no long expositions and speeches, please. We can save those for the wine and cheese. All right? So you can just go ahead and you can line up if you like. If there's somebody at the mic and you want to go next, just go and stand behind them. And I'm going to moderate this in a very light-handed way. We'll see who wants to chime in, and if there's anything I can do to kind of direct things, I will do that. So please, by all means, come on up and we can get started.
Hi, I'm Linda Billings. I work with the Astrobiology program at NASA with Mary Wojtek. I had a question for the writers, the journalists on the panel. I would love to hear what you thought about the proceedings of the day. I'm a social scientist myself, and much of this went over my head, but it's all fascinating. But I would really like to hear from you.
I mean, this is stuff that I write about all the time, and so it's a really great opportunity for me to kind of step back and kind of get an overview of the big questions that are driving the field. It certainly, I mean, it was sort of interesting that every now and then you would see you know, headlines, you know, from slide to slide, and you know, clearly that's a sign of just how important the origin of life is and the creation of life is to the public. You know, there's a fierce appetite for it. Now, when you get into the details of ribose, that's, you know, where the rubber hits the road, and you have to, you know, try to be a good science writer and find a way to keep people's interest if they don't have a PhD in chemistry. But it's worth it. I think it's also useful to have that historical perspective and see that, you know, just how tempting it is to kind of draw too much out of the latest research, you know, you know, I don't know if I've been writing about things like, you know, like those radium creatures, you know, if I've been guilty of that, but it was the New York Times, so anyway.
You know, I would just say Carl does a great job of bringing in the history. He had a story just this last week that had really did a great job. It actually got tweeted out by the History of Science Society. So, you know, doing a good job.
Yeah, I got to say, it's an honor to be here with Carl Zimmer, because he's the best science writer in the subject of the origin of life in the country, for sure. I'm always struck by, whenever I'm at a conference on the origin of life, I think I'm humbled and reminded that there isn't a lot of unity on the answers for these questions, and it sort of reminds you that I think, as someone who observes it, I want to be able to say, oh, it's right around the corner, and perhaps it is, but when I see the divisions among different scientists in this field, it strikes me that perhaps we aren't as close yet. Sorry, Steve. You wouldn't be on one side or the other, would you? But I'm always reminded of that, and so it's a question that it's one of the most important questions in science, if not the most important. But it's one that I hope I see answered in my lifetime, but I don't know if I will.
And I think what I took out of the day was just the ability to sort of track all of these things. I love the fact that we covered so many different topics across sort of like the whole scope of the origins of science. You know, I'm a journalist who doesn't necessarily only focus on the origins of science. So it's great to get sort of like a refresher course. And then the other thing I enjoyed was the visuals in the presentations. You know, for television, we're always thinking of ways to tell stories visually, and I really thought everyone did an exceptional job with that.
Thanks. Okay, yes, hi.
So hi, I'm Jake Mesler from Blue Orbital Space. It's a fabulous event. So my question is mainly for Stephen and David, but of course anyone else who wants to chime in. I want to return to this idea of panspermia, which Steve, you mentioned that possibly we're all Martians, and David, you mentioned that Mars and Venus both had these eras where they might have been water worlds. So my question is there any evidence we have to suggest that panspermia originating on Mars might be more likely than Venus, or vice versa? I'm partly asking from my background as a climate modeler, where we have a much easier time getting Venus to be warm under a faint young sun than Mars to be warm under a faint young sun. But I'm not sure, is there any reason why we would think one or the other? And actually just have a quick question that Stephen might answer is, can you conceive of a planet that might be more conducive to the origin of life than Earth? And might that have any implications for panspermia?
As far as your first question, it's a great question. There might be a slight bias towards Mars in terms of celestial dynamics. I think it's probably a little bit easier or more frequent to transport stuff from Mars to Earth than from Venus to Earth, just because Venus has a bigger gravity well, and so for a given size of impactor, you're going to be less likely to blow chips off that are going to go into orbit and end up at Earth. However, that may not have been the limiting factor. We're talking early on during heavy bombardment, there was probably, conceivably, there was a reasonable flux of stuff going between all of them, so that difference might not be that important. As far as early environments, I'm tempted I'm sort of a Venus guy, and I'm tempted to say, Venus is a tabula rasa. We don't know anything about its early environment. We have some hints, and so for all we know, it could have been by far the best place. Whereas with Mars, we know of some potential problems, and there's some weird unsolved problems of the climate. But in reality, there's nothing we know about any of the three that precludes an origin of life. So I would have to say it's still pretty up in the air.
Yeah, I'm racking my brain trying to figure out a planet that might be more conducive to origins of life. The thing is that planets evolve, so we had to go through the late heavy bombardment, which ended 3.8 billion years ago or something like that. I think most of the planets in the solar system, at least the inner ones, all had the late heavy bombardment, right? So I don't see any way of doing away with that, and it's probably similar if the formation of solar systems is similar in other planets on other solar systems. As I say, planets evolve, and there was a time when there was no oxygen on the Earth, and oxygen, when it evolved from photosynthesis, really was poison, right? So things had to evolve based on that. So I don't know. Do you have any ideas on that, David?
I was sort of glad he directed that one at you. The fact is, my impression from listening to the talks today is, that it's still fundamentally an unsolved problem. And once we know that those requirements really are, we could talk about a planet that meets them better. but at this point, I'm kind of at a loss to say what that would be. Oh, Steve probably has a better idea.
Yeah, I mean, first, the celestial mechanics is all worked out relatively reliably, and you can go look it up. There's a very minor contribution for the fact that Mars is farther out from the sun than the Earth, and of course, as David mentioned, the gravitational well from Mars is much lower. But of course, remember the atmospheric, thickness of the atmospheric has to do with the size of the impactor both coming in and going out. Second, Titan is often referred to as a place where you might have more prebiotic organics. We don't actually have a clear understanding of whether we could have a warm Titan, that is something that's closer. If you have a problem with a faint early sun, it's going to be worse in Titan, which is like 10 astronomical units compared to the Earth. So, but we would be perhaps better to have a warmer Titan with an organic richness, which would be more conducive maybe to the origins of life. But as you know, the four most important words in science are "I do not know," right? So that's where you're focused right now. There's an interesting possibility. And remember, the argument for going panspermia has nothing to do with sort of just, hey, let's go panspermia. Panspermia is invoked to solve particular problems. So as was mentioned earlier, it's invoked to solve the problem that when Lord Kelvin was talking about it, he did not know about radioactive decay. He was saying that if the sun is the best imaginable quality of coal, and we burned it for a certain period of time, we know by the mass of the sun that we can't have had hundreds of millions of years of, and he was working very hard to find ways of increasing the lifespan of sun by having bodies in near solar orbit fall into the sun, converting their kinetic energy. So panspermia is invoked to solve a particular problem, in this particular case about inadequate physics. Here, we suggest that life might have come from Mars to solve a particular problem, which comes from inadequacy of early modeling. But it's water modeling. It's the notion that Earth, having had so much of an inventory of water and so little plate tectonics, that you were not able to get dry land necessary to solve the intrinsic instability of your early biopolymers with respect to hydrolysis by water. But, you know, I just talked to you, where's in 2O, and there's a nitrogen oxide. Oh, there you are. Okay. Yeah, I mean, there's a whole story that you can get if you solve the early Earth, faint early sun problem by better greenhouse effects. It's certainly easier to do on Earth than in Mars. And the facts are that I find it more likely that as we understand early Earth, we get more and more of an understanding of an earlier start to plate tectonics than we have thought about it 10 years or 20 years ago, which means in earlier continents. And so Steve Moyes, for example, is willing to give us roughly 2 California-sized land areas of dry land at 4.2 billion years, which would be more than enough to not need to go to Mars.
Yes. Yeah, I don't know. I'm Anthony Weston. I'm an independent philosopher, and just like to say it's lovely to be here with you folks, many of whom I've read and taught on a few occasions and even reviewed in one case. But here's the thing. When panspermia came up, I thought, aha, this is an opportunity to speak to folks who are all over this field, but central to it in different ways. To just ask you a question about this. Is anybody else bugged by the sexism of it? This panspermia? Like, seriously. So, yeah, we don't have to talk this way. We can talk other ways. For example, panovular. Why don't we try that for a while? I'm totally serious. Or let's say pangermia, where at least, so panspermia or panovular are animalists, right? So, but we could have it might be more sensible to have
I just have to say, yeah, as a feminist, to write a book about the history of this subject, it's needless to say, it's a very, very male-dominated field.
This image of men
was,
going out.
It made me feel bad. It
yeah.
made me feel bad.
Well, we could change it. You folks could change it. But it isn't just that, you know, this isn't just politics. I mean, people are talking here about the conceptual, well, tools of a variety of sorts, including different kinds of telescopes and all, but also the conceptual tools that we use to think all of this through. And so this is a concept, right? It inclines us in certain directions and closes us off from other ways of thinking. For example, if you think of like the panspermists, or maybe us down the road, spreading our sperm all over the universe, then you have to think of other things like planets being impregnable, right? Or not impregnable, but what I mean is pregnable, right? The possibility of making them pregnant. So there's a whole kind of conceptual frame that inclines towards certain kinds of space exploration and not others. So what if it was something that didn't have to do with seeding at all, but something more like invitation, so pan-invitationism. So like the Stephen Hawking project, what is it called, that was sending out the little chips with the...
Nano spacecraft?
Yeah, there's a name for that.
Starshot.
Yeah, Starshot. So is that what kind of, that's not a spermia of any kind, or an ovula or germia or anything. That's a sending out of a kind of an announcement or a sort of an invitation to respond. So it matters what we call this, right? It isn't just that it's offensive to certain people. So I'd like to put that out there as a plea, as well as something people might want to respond to. And the plea is, let's change it. You can change it. You can change it, and we should.
When you started your comments, I thought you were referring to what to me is a little bit of a mostly white male elephant in the room, which is the fact that the gender balance of our panel is not reflective of the gender balance of the gender population or even that of professionals in the field. Which,
that's partly a reflection of budget, I have to say.
Yes, and not to be too hard on anyone, but it is, it's a longer conversation, but it's noticeable, and I personally want to cop to that we all professionals have to try to do a little bit better with that, a lot better, and not to diss any individual or institution. I love you guys, and but it's interesting that the point you did make about language is one. I've heard that critique, and I've always in my mind thought, well, but the root of panspermia just means seed, and seeds are the way that physically life spreads from place to place, and it moves from finds its way to desert isles on Earth, and so. If you look at that root, is that really a gender thing, or is that just a mechanistic thing? But then maybe there's a deeper level in which I'm fooling myself, and we do need to look at that. I don't know.
I would just note that there's a long-standing metaphor in science and especially medicine of seed and soil as an idea for conception of disease and the spread of disease. This was used extensively throughout the 19th century and well into the 20th century. The notion of disease having to fall upon fertile soil in order to take, and sometimes it falls on barren soil, and then you can be exposed to the disease but not get it. So I think it's a really interesting point to think about the gender dynamics of this.
Nathaniel, if I could elaborate on what you're saying just a bit.
Yeah, please, by all means.
I think this question of to what extent rhetoric or discourse is important to the way we think about science is something worth contemplating further beyond just changing the name for something. Of course, what we're trying to do today is talk about what are the conditions of life, what makes life emerge. And the fact of the matter is that the word sperm, as we've already discussed, means seed, but this goes back to Plato. And when Plato talks about where new organisms come from, he says that the form is provided by the sperm or the seed, and then the nutritive environment or the soil is provided by the matrix, which is where we get the word mother. So these are deeply gendered words, but they also inflect the way we think about what counts as meaningful to life. Is it the material substance, or are we talking about something like form or pattern that can be simulated?
Nice.
I believe that ma is an Indo-European word meaning mother, and matrix is derived from mother, not the other way around, but maybe I'm mistaken.
Any further comments on that one, or should we move on? Yeah? Okay, please.
Vladimir Arpetian, NASA Goddard Space Flight Center. So I want to throw a couple of ideas about panspermia by itself. First, if a panspermia really efficient way to seed life, then we need certain concentration of organic molecules of certain complexity to be accumulated in the aqueous reservoirs on Earth. That's the first thing. The second thing, it's more important, is the chirality of life. We know that amino acids are left-handed. So do we know that left-handedness is the universal requirement for life? And so unless we solve this problem, we can't say anything about panspermia.
Well, okay, the Burmese python comes to Florida. Mr. and Mrs. Python are both necessary, and they land in the Everglades, and this is a case where the environment is suited for reproduction, and therefore they take over because they lack a host, predator rather. The other alternative, of course, is they could land in the Everglades and find that they don't have any food, and then they could go extinct. So your problem with being in Mars, right, you're sitting in Mars, you are, say, evolving or originating on Mars because you enjoy, at least your molecules, can survive in a relatively water-poor environment, but at some point you might regard water as a limiting resource, just like many bacteria in the ocean regard iron as a limiting resource, or plants regard nitrogen as a limiting resource. So you're sitting in your sunroom Sunday morning doing the crossword, you get hit by a meteorite and get kicked to Earth. You splash down in an ocean. Now your first possibility is that you will say, hey, this scarce resource, water, which I have been harboring, conserving, and working very hard to maintain as a scarce item on Mars, is all of a sudden now abundant to me, and I will then burst out like the Burmese python has done in the Everglades. The other possibility, of course, is that you have adapted to be in a water-sparing environment, using whatever water you have, and then when you land in an ocean, you just drown. So your first question will be, we don't have a clue in general as to how that works. What was your second question? Oh, right. No, we don't know that L amino acids are, in fact, we can make DNA out of L, which is the opposite of its natural structure. We can make proteins out of D amino acids, and there's no reason, I think, to believe that one is the other. Now, there's a lot of theories on that, right? So the parity violations of nuclear decay, the optical polarization of circularly polarized ultraviolet light, these have all been invoked, but we don't know.
I actually have a reaction to the chirality question that I sort of want to bounce off some of the more chemically literate people here, like Steve, for instance, which is that it always seemed to me like something that people work really hard on a solution for that's not really a problem, and that, I mean, I understand why like having a chirality is necessary for stereochemistry, but it seems to me likely to just be sort of an arbitrary random thing that happened in, you know, when this origin of life thing was happening, and then could have been either way, and then once it started, it self-perpetuates. And so it seems sort of very unprofound to me, the left or the right, that if I mean, stereochemistry makes sense, and if there's organic life other places, it probably uses a chirality, but it seems to me likely to just be sort of random and not that hard to sort of pick one and then get perpetuated. Is there really, does there have to be more to it?
What Francis Crick would have called a frozen accident.
Yeah. Yeah, as far as I understand, the number of meteorites, the chemical analysis shows that number of meteorites show excess in L. That's really...
Well, it depends. I mean, the meteorites that show excess are, I mean, Sandra Pizzarello, George Cooper at NASA Ames. These people have found asymmetric excesses of one over the other. And the problem that most of the times that they find them, they have what they call alpha methyl amino acids, which are amino acids that are not able to lose their chirality quite so easily. But yeah, I mean, I agree with you, David. I mean, basically, homochirality is essential for biopolymer evolution. And that's because when you evolve and replace an amino acid, you really don't want to do you want to do a side chain replacement. You don't want to do a side chain replacement at the same time as you do an orientation change. And so homochirality is important. But I suspect, and again, the words are I don't know, but I suspect that you pick one or the other, homochirality being important, and then which you pick is going to be. And of course, we'll be very fortunate when we discover life on Mars that it's the other chirality, just that will show that we're not necessarily contaminating the sample that we looked at on Mars with something from Earth.
Well, my proposition might be there is a certain anisotropy, that, for instance, related to the magnetic field, to the polarized electrons, to some environment that creates certain predisposition, certain excess.
Okay, well, there's between 10 and 100,000 paper literature on this particular subject. So circularly polarized ultraviolet light in the Sagittarius Nebula is preferentially one over the other, and that could be a intrinsic source for chirality in that location. Okay. People, 10,000 papers might be an underestimate.
Let's get on to another question here.
Which were formed in supernova explosions in a series of generations. The universe formed about 15 billion years ago. It takes a few billion years for a star to form, go through its life cycle, and finally explode. You need several generations before you get to atoms that are heavy enough to perhaps support life. Do we have any estimates of when life could first have been formed from that point of view? Is it possible we are the first life because of that limitation?
I'm totally unqualified to answer your question, but one thing I will note is that there's some, I think his name is Abraham Loeb at Harvard, has come out with a neat paper actually suggesting that if you look at these processes and you look at the lifetime of the universe, that you'd really expect life to originate a lot far off in the future from now, like billions of years in the future. So the suggestion being like, why is it so hard for us to find life on other planets? Well, we're like that person who showed up at the party too early and you're like, oh, there's nobody here. We showed up too early. This is a paper that's on ArcSci. You can probably muck around and find that. So
we could be the first.
Yeah, no, this is actually a statistical argument that yes, we are the first.
Yeah, the paper that I've seen is you are, every one of your interesting atoms, your molybdenum and so on, you are the product on average of 3 to 4 supernova that you have been through, so you are a star child 3 or 4 times. And yeah, I mean, of course, the only thing is that the metallicity, as we like to talk about it, is asymmetrically distributed in the galaxy. And so, we should be looking, and people do that, right? People look for high metallicity stars, which have presumably had more generations to create the heavy elements. But you are the product of 3 or 4 supernova, and 25, what's the story? 25 light years away, 4.5 billion years ago, a supernova exploded. The shock wave is what caused the collapse of the solar nebula to produce you. Congratulations.
You too.
All right. Yes?
Yes, my question is about the news article which appeared recently on the earliest form of fossils ever discovered. I think David showed a picture. In that article, they had a photo from Shark's Bay in Australia. So I'm looking at this thinking, I'm to believe that the oldest form of life is still here. It's gone through all the eons of change, and it's still here, looking just like it used to 3.7 billion years ago. I'm thinking that seems pretty unlikely, or it does say that life is extraordinarily stable, or I'm misunderstanding something.
Well, this was really a biosignature of, these aren't even actually fossils, right? They're the remains of fossils.
No. Well, maybe they showed the picture just to show you what a modern stromatolite looks like, because there are still stromatolites around, and so this was a stromatolite back then. So, I mean, like it's a if it ain't broke, don't fix it kind of situation. I mean, it works pretty well. And it's still around. They're not as common as they used to be, mostly because animals showed up and just ruined the neighborhood. I mean, they used to be much more common. And so actually you have to look harder for stromatolites than you used to. But, it doesn't
strike you as meaningful that a stromatolite happens to be the very first form of life.
No, it's not the very first form of life. It's the oldest form of life that we have found. And that does speak to the fact that there had to be hundreds of millions of years of evolution to get to that point of cell. Those are presumably cells with DNA and protein in them, and with communities of different species interacting, cooperating. Yeah, that's no small feat, but there could have been hundreds of millions of years of evolution leading up to that point. This is just the oldest sign of life that people have found so far. 3.7 billion years ago, the Earth had been around for 800 million years already. So.
And when you say the earliest form of life, I mean, there's a truth to that, but it's different from like finding a giraffe that's 3.7 billion years old and saying, oh wow, that's a long-standing form of life, because a stromatolite is not an organism, it's a microbial mat. It's a way of a community of microbes deciding to live together in sort of a horizontal arrangement. So there's potentially an argument for sort of from almost biophysics for a kind of universality of that. In fact, people talk about looking for stromatolites on Mars, actually. Maybe that's a stretch, but it's less of a stretch than talking about looking for a giraffe on Mars, because there's sort of a basic almost physics or basic sort of geometry to why simple life might arrange itself in that way on a planet. Yeah, it's an architecture.
Well, I want to encourage your sense of skepticism, because I passed a stromatolite around and I got it back and nobody remarked to me. He says, what the hell do you think you're doing trying to tell me that this is a remnant of a life form? Right? There's a rock, and it's a rock with precipitated material in it. So what you're observing here is the precipitated inorganic, insoluble material, and we want to encourage you to ask the question when you encounter somebody like me saying to you that's life, as how could you possibly know that? Now, they know it, right? There's a lot of work that goes into that and many, many PhD dissertations, but yeah, I mean, that's a good sentiment to have, right? When someone tells you that there's 3.7, for example, how do you know whether it's 3.7 billion years? And the answer is, well, there's an answer to that question. I think it was actually in the paper. But yeah, these are the kinds of questions that you should ask. And of course, that's where we try to train the students to go deeper so that we love asking PhD candidates, you think water is H2O. What's the primary data that say that, what are the primary data that say that water is H2O?
And there are some quote unquote fossils from almost that old that people don't think are fossils anymore. That they looked a lot like them. It gets very tricky with things like microbial mats that old. It gets really hard to figure out what's living and what just is rocks that look like what you'd expect. But yeah, it seems like this new one, I don't know, people seem to be pretty solid on it, although you think so? All right, he thinks.
I don't know, no, don't listen to me. I'm not, I mean,
if I had written the article, I would have called you.
If you go over to the Smithsonian today and go into the Natural History Museum, you still see Bill Shopp's carbon specks, which we thought used to be cyanobacteria, which we don't think are there. They're still in the Smithsonian as the earliest example of life.
Okay.
Right by that big elephant.
Yes.
Hi there. I'm with the Richard Dawkins Foundation and the Center for Inquiry. And my question is to you scientists and science communicators. You still have to operate within a political environment. And it determines what resources you have. It determines whether you have freedom of inquiry. So I'm asking you what is the current status of the political environment in which you operate, and are there any danger signs that you're concerned about down the road?
Oh. Let's keep this nonpartisan. Everybody's passing.
I don't know why people are handing me the microphone. Yeah, that's right. Personally, I mean, I'm hesitating because I don't feel like I have a really profound, I think it's an important question you ask. With this particular area of inquiry, I don't feel a lot of political pressure. I mean, out there in our society, there are the forces that, want to teach, that are concerned about teaching evolution in the schools and, all the stuff that you guys at the Center for Inquiry are very well aware of. And those, those are things we're aware of, but they're not, it's not affecting our ability right now to do the research we do. It's certainly, affecting our ability to, in a larger sense, communicate and have a science literate society, which is a wider concern. And of course, in my area of astrobiology, which has to do with climate modeling, I'm working with people who are feeling the effects of some of the slight, inquisition-like aspects of some corners of our government's approach to climate modelers. And so, there are some danger signs on the dashboard, some lights flashing. But as far as there's nobody telling us not to research the origin of life or anything like that. There's no sort of acute political constraint on this area of inquiry, but I think, as members of a society at large that concerned with science and education, there are certainly some things we need to pay attention to.
Can I turn the question back to you, although you seem to have disappeared? You work at something with Richard Dawkins in the name, so what is your experience?
Well, I run the Richard Dawkins Foundation for Reason and Science, and we promote atheism and scientific literacy.
So you have a more direct contact to the public than perhaps. I mean, I talk to
it's often
Society. I talk to creationists all the time, but you have a more closer contact to this. And what's your experience?
I work in a realm where I'm trying to debunk mythologies, and people cling to those ideas and are very hostile to anyone who challenges them. I would say when you're dealing with pure science, it's easier to put forth ideas. Often, to be perfectly frank, they're a little over the head of most average people, lay people, so they're not going to be challenging you directly. But we run a program, for instance, the Teacher Institute for Evolutionary Science, where we teach middle school teachers how to teach evolution. And we receive, on a daily basis, responses from teachers that say they can't teach the subject, that kids will turn their chair to the wall rather than listen to something that defies what they've been taught by their pastor, their priest, their minister, their imam, the rabbi.
Would you say that's increasing, decreasing? Do you have any reason to make a statement?
Well, I don't know. I mean, I do know that 43% of Americans say that human beings arrived on this earth fully formed within the last 10,000 years.
I mean, because I talk a lot to the Gainesville creationist community. I just gave a talk, what religion is that science, what science is that religion is not. The subtitle for that talk is, and why scientists do so very little of it. But the bottom line is that they're nice people. They don't seem to be, I've not encountered hostility. Of course, the public, even the creationists, very much values the technology, the new medicines, the new, therapies and stuff that is coming from science, as whatever that is. Many of them are more concerned about whether their daughter is going to come home pregnant, or they're going to be, they're worried about the social decay. They're all worried about all sorts of other things for which origins of life or evolution is a proxy, right? It doesn't really, it's an assault on authority. They don't actually much care. There's no constructive reason to care one way or the other when the Earth was formed. I mean, how does it influence their daily life? But it does influence their daily life that their kid come home drug addicted, for example, and they're worried about the loss of authority that would tend to prevent drug addiction. At least that's how they view it among their children. But so you actually think that there? I mean, is it?
I think there are direct societal consequences to that kind of scientific illiteracy in the general population.
Well, I agree with that, but
and I think that there are consequences for resources for science and public policy, from stem cell research to, abortion rights to same-sex marriage to climate change. So, and I wish scientists would get a little more engaged in these battles, because we need you.
Okay, we have a couple of repeat questions. I want to get the people who haven't asked a question first, and then we'll get to you. So, yeah.
Okay, and that is, we've spoken about the origins of life and the difficulties of defining life. And we've talked about DNA, RNA, but it seems to me that at least what I think is what's really interesting, the really interesting life on Earth, the people all around us, is eukaryotic life. And can we imagine intelligent life arising with life forms that have not experienced a eukaryotic threshold? Is there some other path that people have at least thought about?
Meaning, is a membrane-bound nucleus necessary for higher
For
intellectual processing?
interesting multicellular life.
For the development of a neural system or something like that?
Because, I mean, you know, we're thinking about, you know, the first step. We've got microbes. Hooray, we've got microbes, which is most of what we've had on Earth. But the part that makes our heart beat is when you start getting eukaryotes and multicellular life and complex life with tissues and organs. And I'm wondering, has there been any thought given to how complex life with tissues and organs and this sort of thing might have arisen in the absence of a eukaryotic threshold?
Let me throw in there, just into the mix, whether that question really is about the transition from one of the major forms of information exchange being lateral gene transfer, shifting toward a more vertical gene transfer in the invention of sex. Possibly another way of phrasing the question.
I just also like to add that some of the things we talked about recently, the stromatolites, the biofilms earlier today, horizontal gene exchange, all of these are, perhaps they don't immediately translate into intelligent life that can send out signals to other planets, but these are the beginnings of differentiation, and these microbial communities are working together at some scale, sensing the environment, having feedbacks with their underlying biochemistry, and differentiating. And so even before you have nuclei, you have systems reacting to the environment and differentiating in ways that are more complex than they can individually.
Biofilms can be differentiated into different kinds of...
Yeah, I mean, exactly.
As you were saying.
You know, what facilitates the layering in stromatolites and what facilitates antibiotic resistance amongst biofilms in many cases. So there's a lot of evidence of these microbial communities working together in that sense.
Let me see if I'm assuming that you would like the story rather than the statement, we don't know, right? So here's the story.
I know we don't know.
You know we don't know.
Has somebody thought about this more than I have?
Oh, sure.
So here's the story. Multicellular life emerged. We don't quite know well. The Cambrian explosion is a very clear statement as to when fossilizable forms 542 million years ago is the number. And the story is that that's associated with the rise of atmospheric oxygen, right? Because the argument is that oxygen, O2, and oil, that is lipids, have a huge potential energy difference between them, hence you run your car by burning gasoline, and that multicellular life requires that huge amount of energy, and therefore multicellular life required the emergence of atmospheric oxygen. Second point is atmospheric oxygen is almost certainly arising from photosynthesis. The cyanobacteria that we talk about are generating dioxygen into the atmosphere. And you can look at maybe 2.5 billion years ago. There's a little rise in oxygen, but the real ramp up of oxygen is roughly the same time as the emergence of multicellularity. Eukaryoticness, which is a different, you use that word, right, the idea of this nucleus membrane having a differentiated cell and all the rest of it. Is it required for multicellularity? Well, any good microbiologist will tell you that unicellular organisms, by forming these mats, and you just said this, are multicellular in some sense of the term. But an organism of the fine specimen of multicellularity that you are, with a backbone and the ability to walk, without an exoskeleton so you can grow without having to shed your skin and all the rest of these things, this is something that is argued to be associated uniquely with eukaryotic life based on the ability to have sex, which you've just heard, and that's an important way of increasing the rates of evolution for adaptation. Now, the second question is you have to do about likelihood, right? Let's just, speak in round numbers, the sun will last for what, 10 billion years, but the sun will grow to a red giant and consume the orbit of the Earth and make Earth uninhabitable, say, after 5 billion years. I'm speaking around. So you can say, I got life on Earth within the first 15 seconds after the Earth emerged in terms of microbes, but it took me 4.5 billion years to get the fine specimen that is now standing at that microphone, which just means that the sun is almost done with you, right? So you can say that microbial life is easy by that metric. Fine specimens of life able to use this microphone are difficult by that metric. But in order to have intelligence and the ability to communicate is a very rare item, because at least on Earth, it took a long time, most of the life of the habitability of this particular rock, for it to emerge. How does that do for you?
Thanks to both of you.
Okay. One more here, and then we'll do round two.
Yeah, I just want to add that in the next billion years, the sun will increase its luminosity by 10%, and we're going to start to see the effects of the runaway greenhouse. It's a 10% every billion years.
Okay.
In a billion years, so we don't need 10 billion years.
When should I move back to Mars?
In a half a billion years to be. Yeah, but what I want to say, it's just a comment to the question about when universe became habitable. There is a paper written by Mario Livio from Space Telescope Science Institute. He did calculations of production of carbon, oxygen, and nitrogen as a result of the 3 alpha reactions, and then iron and more heavy elements. So you need at least 7 billion years. So that's so basically we're halfway through. The first half a billion years, the universe was completely sterile. So we're lucky. We're not lucky. It's just probably the right place to be here. So just a clarification. The paper is there. I can give a reference.
Okay.
Thank you.
All right. Yes.
My question is for Sophia. We saw earlier with one of the first questions and in your talk that the way we talk about science and the way scientists do experiments to fit narratives can change how those explorations are investigated, right? So looking at synthetic...
How the what is investigated?
So looking at synthetic life, we can't get something to work, so we simplify it and then make it fit the model that we want, right? So during your ethnographic investigation, you investigated synthetic biologists, right?
Yes.
And so did you find any other cultural or rhetorical biases that were similar to that?
Many, although with the caveat that I wouldn't refer to them as biases.
Sure.
Science is cultural and social all the way down.
Sure.
So of course, whenever we look at how scientists are thinking about the living world, you will see aspects of society and culture in them. That's the reason why we have a field like the history of science.
So more salient ones, I guess.
Yeah, so there are a number of things that I identified throughout my 8 years of ethnographic research. One of the things that I found most intriguing was the ways in which something really simple like biological relatedness, right, otherwise known as taxonomy, has to be radically reconfigured when it comes to talking about microbes that bear genes that come from diverse organisms, right? So what is that? Where does that fit on the tree of life if it has, you know, using the examples that I talked about in my talk earlier, genes from petunias or hyperthermophiles or something else? And this was something that was a live question for many synthetic biologists, and the ways in which they discussed it drew upon a lot of social and cultural assumptions about how people are related to one another, but also about what the ground for how we would think about living relatedness, or even a category like species, is defined over time. And I think at last count, I read a paper that said that there are more than 57 working definitions for what is a species as of, I think, 2 years ago. That could be found in the scientific literature. So terms like that are incredibly capacious, and they mean different things depending on what subdiscipline you're from.
Thank you.
All right, we have time for one more question, I'm afraid, and then we can have further informal conversation during the reception. So we'll give this one to you, Jake. I'm sorry, but we can grab the speakers over a glass of wine. All right? Yes.
Professor Roost, in your talk, you quoted a scientist who said, "I only understand what I create." And of course, I immediately thought, what if you create something you don't understand? And I'd like to take that then to Professor Grinspoon. You have great optimism about the what did you describe, the sapient zoic era. And, you know, when we think about the vast explosion of knowledge that we've had in our lifetimes, you know, I tend to be optimistic, but is progress a comfortable disease? And we are at a point, certainly we learned recently that man can induce earthquakes. And so are we perhaps entering into a strange new world here? And I just open that up to anybody.
Well, it's interesting. I love the two parts of your question, because in a certain sense, our problem right now is that we've created something we don't understand with our global technological civilization and its effect on the world. So there you go, Richard Feynman. You know, and I just want to say, you know, you referred...
Clarify for a moment. What Feynman wrote was, "What I cannot create, I do not understand." Which is a very different kind of claim. This is about how making something furthers a more comprehensive and deep understanding of it.
Right. So that doesn't imply that everything we create we can understand.
Not at all.
Yeah. Okay. That's thank you for that clarification. But you know, in relation to optimism, I just want to say it's complicated. And I actually, part of my book, I have a whole taxonomy of pessimism and a whole taxonomy of optimism, where I kind of break that down a little bit, because I don't see it as binary, although people tend to. And I certainly don't want to minimize the challenges of the next century or a couple centuries. You know, they're huge. But I do think that with climate change and so forth, and the possible, you know, some of the bad scenarios where you see sea level rise and a lot of displaced people and refugees and all that, we're talking about the 21st century possibly being as bad as the 20th century, where if you think of the wars and the famines and the mass displacement and so forth, I mean, you know, we made it through the 20th century, so we think, oh, that wasn't so bad, but it was for a lot of people, right? And so I think, you know, climate change is this wave that we're sailing into now. And there is another side. There will be a human race and some sort of global society. So it's not an either or. People tend to think of it as an either or. It's a trajectory. And you know, human beings have two ways of learning about things. There's the good, to simplify, there's the good way where we see what's coming and we anticipate and we take corrective maneuvers. We're not so good at doing that collectively. And there's the bad way where we react to calamity, right? And it's going to be some combination of the two. And so it's a complex range of trajectories that we're going to navigate. And there is another side. And I think that even with some of the bad scenarios, there's ultimately a glorious future, but not without some pain and casualty. So I am, in a long time scale, I'm optimistic, but that's actually fairly qualified.
I would just add that, I mean, one form of life that we haven't talked about is artificial life. And so there's a case where you're trying to build something, and you know you're totally in control as the scientist, you know, programming a computer to have like virtual life forms inside of it. And you know, there are people at Michigan State who have developed a system called Avita, where they basically let these systems evolve, basically little programs to evolve to solve problems, adding numbers, doing math, doing all sorts of things. And you know, it's all deterministic. You can see exactly what happened, and they followed all the principles that you built in of sort of an evolution happening in the computer. And then they get this thing that works, and then they try to look at it and understand how it works, and they don't understand it. They can't. It doesn't look like a computer program any human wrote. And they can't. It's very hard to figure out how it works, and so I don't actually think that being able to create something is a guarantee of understanding it. And you know, maybe the future, like the machines, will be replacing us. And if we program them with evolutionary principles, we have no idea how they're going to be working a billion years from now. And then they can just go off into space and not worry about the sun burning up, I guess.
Okay, I think that's an optimistic note on which to end. So I would like to, Janice, did you have a? Yes, okay. Well, I just want to thank you all once again for participating and really making a very lively, multidisciplinary day. I've had a great time. Thank you.
Well, this was something. Today's symposium really has given us a lot of rich and diverse food for thought. And if you're like me, you probably want another opportunity to mull these things over and think about them and hear some of the discussions again and listen to the questions and the answers again. And fortunately, you will have that opportunity because in about 6 to 8 weeks, we hope, this will be available. The programs were taped today or recorded today, and they will be available on the library's website, which is loc.gov, as well as the Kluge Center website, loc.gov/Kluge. So you will have another chance to reflect and think about these things. So in closing, I would like to thank all of the participants in today's symposium for their thoroughly engaging and thought-provoking presentations. Thank you all. But I would especially like to thank Nathaniel Comfort for organizing this event and for serving as a catalyst for such an exciting exchange of ideas. And it has been a privilege to have you here at the Kluge Center. Thank you all for coming today, and please join us for some refreshments and to continue the conversation.
This has been a presentation of the Library of Congress. Visit us at loc.gov.